could be familiar with pi and infinity, but have you ever paused to consider how remarkable they are? The film A Person of Interest explains the enormity of pi much better than I can.
Pi. Can any of you tell me what it means? I'll settle for an intelligent question here. Yeah.
My friend has a question, Mr. Swift. What is any of this good for, and when would we ever use it?
Let me show you. Pi, the ratio of the circumference of a circle to its diameter. And this is just the beginning. It keeps on going forever without ever repeating, which means that contained within this string of decimals is every single other number. Your birth date, combination to your locker, your social security number, it's all in there somewhere. And if you convert these decimals into letters, you would have every word that ever existed in every possible combination. The first syllable you spoke as a baby, the name of your latest crush, your entire life story from beginning to end, everything we ever say or do, all of the world's infinite possibilities rest within this one simple circle. Now, what you do with that information, what it's good for, well, that would be up to you.
Other numbers in the countdown will be unfamiliar to you. So, for example, E is introduced to you in year 12 when you study logarithms. If you plot the graph of y equals e to the x, the value of y for each given value of x is also the same as the gradient at that point on the curve. You know from GCSE that you can't take the square root of -2 because there are no numbers. So in year 13, you'll be introduced to a new set of numbers called complex numbers that does allow you to take the square root of negative numbers. Okay, let's do some maths then. In a minute, I'm going to show you a question, so pause the video and then have a go at finding the solution to that question. How did it get on? We're looking at just 4 points initially. We're looking at 0, 0, a squared, b squared, and c squared, all on the parabola y equals x squared. It mentions that the two lines are parallel, so it may have something to do with the gradient of the lines. If you can remember from GCSE, we can find the gradient between 2 points by doing y1 minus y2 divided by x1 over x2. So the gradient of the line AB is equal to a squared minus b squared over a minus b. If you notice, the numerator there is the difference of two squares. We can factorise that to be a plus b multiplied by a minus b. That means that a minus b is a factor of the numerator and denominator, and so simplifies to be 1. So we end up with the gradient being a plus b. We can also look at the gradient of OC. So we've got 0 minus c squared over 0 minus c, which simplifies to be c. As the two lines are parallel, we know that the gradients must be the same, so a plus b equals c. The second part, we had two new points to consider, d and e. If the x value is d, then the y value is d squared, as we know it's on the parabola y equals x squared. We can also calculate the gradient of the line DE as it's parallel to the other straight lines. We can also deduce that D plus E is also equal to C. Then what we have to do next is to remember how to calculate the midpoint between two lines. So we have to add the x values together and divide by 2, and then add the y values together and divide by 2. So the midpoint of OC, we've got 0 plus c over 2 and 0 plus c squared over 2. So the midpoint is c over 2 and c squared over 2 for the y value. The midpoint of line AB, we can do the same. But if you remember, a plus b is also equal to c, so the x value is also equal to c over 2 for the midpoint of AB. The midpoint of DE, we end up with d plus c, which is also equal to c. So the midpoint of DE also has an x value of c over 2. As the x coordinates are always c over 2, we know that the line x equals c over 2 must pass through the midpoints of the three lines that we had on the parabola. Okay then, question 2. I want you to find all the solutions to x squared minus 7x plus 11 to the power of x squared minus 11x plus 30 equals 1. Now this won't look anything like anything you've done at GCSE, so I'm going to give you a bit of a hint here. All the maths you need is within GCSE knowledge. And your clue is, when does a to the n equals 1? So what are the cases when a to the power of n equals 1? Okay, again, pause the video and have a go at this question. How to get on with this then? I think a lot of you may have struggled with this. Some of you may have found some of the solutions, and hopefully some of you have found all the solutions to this. The first scenario when a to the n equals 1 is when n equals 0, apart from when a equals 0. So we can say that x squared minus 11x plus 30 is equal to 0. Factorising that, we can see the solutions we get are either x equals 5 or x equals 6. If we substitute that back into a, we can see that it's not equal to 0, so we know that 5 and 6 are both solutions. The second case when a to the n equals 1 is when a equals 1, as 1 to the power of anything is always equal to 1. So x squared minus 7x plus 11 equals 1. If we rearrange that, we get x squared minus 7x plus 10 equals 0. Factorising that, we end up with solutions of x equals 5 or x equals 2. There is a third case when a to the n equals 1, and that's when a equals negative 1 and n is an even power, so negative 1 squared is also equal to 1. If we substitute that in, we get x squared minus 7x plus 11 equals negative 1. Rearrange that, we get x squared minus 7x plus 12 equals 0. And factorising that, we end up with either x equals 4, in which case n is equal to 2, which is even, or x equals 3 and n equals 6, which is also even. So we have the solutions x equals 2, 3, 4, 5, and 6. Now that's quite a neat solution to something that does look really complicated. Now we know that 2 can't equal 1. Can you see the step that causes the problem here? It's when we divide both sides by a minus b. As a minus b equals 0, we're dividing by a 0 which has no solutions. If you've never done this before and you have an iPhone, ask Siri to divide 0 by 0. I also want to show you that maths can be beautiful. And let's apply some logic as well. So we've got 3 people here. We've got Adam, Ben, and Claire. Now Adam can only see Ben, and Ben can only see Claire. Adam doesn't have a maths A level, and Claire does have a maths A level. So can we say, without knowing about Ben, is there a person without a maths A level looking at a person with a maths A level? Now at first glance it looks like it cannot be determined, but there's only 2 possible solutions. Either Ben does have a maths A level, in which case Adam is looking at Ben, or Ben doesn't have a maths A level, in which case Ben is looking at Claire, which fits the question. So yes, we can say for certainty that there is a person without a maths level looking at a person with a maths A level. Now if we look at some patterns, a Sudoku problem is quite complicated, but if we make it even more complicated by almost making it 3-dimensional, we can see here that the small squares in the top row contain the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9, the same as a normal Sudoku problem. But the medium-sized squares and the large squares also contain the numbers 1 to 9. If we now look at a 3x3 grid, we can also see that in the top row of that 3x3 grid, we also have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a really complicated Sudoku problem. If we then play paint by numbers and colour in order number 1s, we can see kind of it visually what it looks like. Each row, column and 3x3 grid has exactly 1 small square, 1 medium-sized square and 1 large square shaded in the same colour. If we continue this to look shading the 2s in a different colour and the 3s in another colour, 4s, 5s, 6s, 7s, 8s and 9s, we end up with a pattern that it looks random, but it also kind of feels right. There's no repeating here going on in this pattern, but it does seem to make sense to us. Okay, let's meet the teachers that will be teaching you next year.
Hi, I'm Mr. Kennedy, and I've studied maths to degree level at the University of Leicester. I was also an accountant for 20-odd years, and I still can't answer the question that was in the person of interest video about what is this topic useful and when will we ever use it.
Hi, I'm Mrs. Dodson. I studied maths at the University of Sussex down in Brighton, and I love being down by the sea. I'm the kind of person that has biscuits in my glove compartment of my car.
Hi, I'm Mrs. Russell. I did my maths degree at Durham University, and
I've been teaching at Boswell's on and off for 20 years.
Hi, I'm Mr. Colton. I've got a maths degree from the University of Reading. I've been teaching for 10 years and all that time I've been teaching A-level.
Hi, I'm Miss Legg. I did my maths degree at Southampton University many years ago. I've been teaching for 25 years now. I've only been at Boswell's since Christmas, but before that I was at the Sixth Form College in Colchester for 5 years.
Entry requirements for maths and further maths at A-level differ slightly. For the maths A-level, the requirement is a grade 6 at GCSE, but a 7 is more desirable. It just means that you can access a little bit more right from the start. For further maths, the requirement is a 7, but similar to maths, realistically, you're going to find it a lot easier if you have an 8. Now, in terms of internal exams, so throughout the course on both maths and further maths, you will have end of topic tests. And then there will be more formal mock exams sort of spread throughout the year. I'm going to first talk about the maths A-level. So the external exams for the maths A-level, all the formal exams are taken at the end of year 13, and there's 3 exams, all 2 hours long. 2 of those are pure maths, and 1 of those is applied maths. Now, those can be a complete mixture of year 1 and year 2 content. So there's no, even on the pure papers, it's not a case of one of them's year 1 and one of them's year 2. They're both years. So here is what year 1 would look like in terms of content. Now, there's obviously quite a lot here. What I want you to realise, though, is that if you look at the pure content, the first sort of 5 sections, realistically, you will have done at GCSE. Maybe not quite to this extent, but the vast majority of you, especially if you are on sort of a grade 7 or higher, those first 5 topics there will be pretty straightforward for you. The circles, algebraic methods, that's where the maths really starts to get interesting in terms of realising how things can be manipulated algebraically, and it sort of gives you an idea of where things are going to lead to. We then go on to binomial expansion, and then into trigonometry, vectors, and then we get onto the calculus, which is differentiation and integration. The final bit of year 1 is probably one of the trickiest bits, which is exponentials and logarithms. If some of you speak to some of your parents, they may tell you that actually they've done exponentials and logarithms when they did their versions of GCSEs. The applied section is actually split into 2 separate parts, which is statistics and mechanics. And if you look at data collection, measures of location and spread, representation of data, correlation, probability, statistical distributions, and hypothesis testing, they are all the statistics. The last 4 there, the modelling in mechanics, constant acceleration, forces in motion, and the variable acceleration are mechanics. Now, the statistics, a lot of it, again, is just a little step on from GCSE. The statistical distributions and hypothesis testing is the stuff that's pretty much brand new. with the mechanics, you will actually recognise a fair bit of the constant acceleration and possibly even the forces in motion from your GCSE physics. But then the variable acceleration is solely in A-level maths. So that's year one, and then at the end of year one you would have a test on the content of year one to make sure that you are okay with that before obviously moving on to year two. Now year two, I won't go into too much detail here as I did on the first one, but you will see a lot of things that are very similar. So algebraic methods again, binomial expansion again, trigonometry again, differentiation again, integration again, vectors again. So there's a lot of things that are basically moved up another level in year two. There are some extra little bits that are quite interesting, things like functions and graphs, sequences and series, a brand new measurement for angles, which are called radians, and so on. You've also got something called numerical methods, which actually you will have seen some of already when you do iterations at GCSE. The applied, like before, is sort of split into statistics and mechanics. This time round, though, the top three are the statistics and the others are the mechanics. Again, the only thing that I would say with this one is that pretty much everything that you look at in year two applied is going to be brand new information for you, not that you'll have seen before. The mechanics, you may find similar things in the physics A level, but actually we do things more mathematically, whereas I think in physics it's a lot more theoretically. Now for further maths, so this is a different qualification in addition to the maths A level. For further maths, you will again have the external exams at the end of year 13, and there will be 4 exams this time of an hour and a half. 2 of those will be pure maths papers and 2 of those will be applied maths papers. Now the way that the further maths is made up is slightly different to the normal maths. So there are some compulsory parts. Everything that we've done in the normal maths is all compulsory, so every school across the whole country will be doing exactly the same. Further maths is slightly different. So you get the core pure, which everyone across the country does the same, okay, and that's the further maths. And you can see here that we've got year 1 and year 2 content. And again, similar to the normal maths, you can see that there is a lot of progression from year 1 into year 2. So we look at something called complex numbers in year 1, we look at it more in year 2. We look at series in year 1, we look at it more in year 2. Volumes of revolution, again, we see it in both years. Now in year 1, I'm going to concentrate on something where we're looking at something called matrices. And that is something that if you access the further maths GCSE, whether that be through the videos that I've been putting out, or whether that be as an external candidate, you have done it within your school, you will see matrices for the first time. They are essentially a different way of representing a set of numbers. But obviously we can do some manipulation with those. In year 2, we look at things like something called polar coordinates, which is a different way really of representing graphs on a circular set of axes rather than a rigid sort of x and y axis. And we move on to something called differential equations. Now differential equations and modelling with differential equations are the key to most of the world's financial institutions. Anyone working in anything insurance based will need to understand differentials and differential equations. Clearly there are other things that they are used for. They are also used to model harmonics. So those of you that are interested in music in a very theoretical manner, differential equations may appeal to you there. So the applied section is where things really change. Different schools can take different options. Now these are the 3 options that we as a school would potentially teach. Now, there are 2 out of these 3 that we would teach. And the way that we decide is I generally look at how the class of further mathematicians is made up. Now, every year we will almost certainly be doing the further statistics. That is something that really, when you look at the normal maths and the statistics, the further statistics is sort of a step up from that, but it's a logical step up, and many find it more interesting once they know how it all works. The other 2, the mechanics and the decision maths, the decision on whether we take one or the other really depends on whether we've got a majority of physicists, those that are taking physics A level, or a majority of computer scientists, those that are taking computer science at A level. The mechanics relates a lot to the physics, and there are quite a few overlaps, especially with the work, energy and power. With the decision maths, there is a lot of overlaps with computer science. So algorithms, route inspection, linear programming, that's all in the computer science as well. So from that point of view, it will change year on year. That decision will be made by myself, not by those within the class, but I will make that decision based on those in the class. Should you have any other questions regarding the content, please don't hesitate to email and get in contact, and I will try and answer any of those.